video we'll talk about alternating series. So first, let's remember that sum as k goes from 1 to infinity of 1 over k, which is 1 plus a half plus 1/3 plus 1/4 plus dot dot dot. It's a harmonic series and it diverges. We talked about it in another video. Now, sum as k goes from 1 to infinity of negative 1 to k plus 1 over k, it's an alternating harmonic series. And let's see what happens. Is it diverging? Is it converging? But if I give a few values just to see how it looks like, if k equals 1, we get 1. If k equals 2, we get negative 1/2. If k equals 3, we get plus 1/3, minus 1/4, plus 1/5, and so on. So basically, in order to figure out what happens to the series, we are trying to find out what happens to the sum of the sequence of the partial sums. So s sub 1 is 1, s sub 2 is 1 minus a half, is the sum of the first two terms, which is a half. S sub 3 is 1 minus a half plus 1/3, which is 1/2 plus 1/3, which is 5 over 6. And so on, which are actually plotted here. So this is the x-axis or the n, and this is the s sub n. So 1 is here, a half is here, 5, 6 is here, and so on. And if we look what's going on, what's the pattern here, it seems like all the eventually, as n is increasing to infinity, this s sub n is going to approach 0.7. So how are we going to do that analytically with other type of series without just plotting the points, right, and looking for the series of the sequence of the sums, of the partial sums? So we have this theorem of the alternating series test. So the alternating series, every time we see this term negative 1 to k or negative 1 to k plus 1, that should trigger the alternating type of the series. So sum as k equals 1 to infinity of negative 1 to k plus 1, a sub k converges provided a, the terms of the series are non-increasing in magnitude, so I want you to think they are decreasing. So that means the a sub k plus 1 is less than or equal to a sub k. And the limit as k goes to infinity of a sub k equals 0. So we have two things to check all the time. So keep that in mind. So the theorem alternating harmonic series, because this one shows up in many applications, it has its own name. So sum as k equals 1 to infinity of negative 1 to k plus 1 over k, exactly, we got these terms, right, converges even though the harmonic series sum as k equals 1 to infinity of 1 over k diverges. So the very first example that we have is determine whether sum of k equals 1 to infinity of negative 1 to k plus 1 over k to the second converges or diverges. So basically, if we look at the terms, right, so just take, if k equals 1, we end up with 1. If k equals 2, we end up with negative 1/4. If k equals 3, we get 1/9. And if k equals 4, we get negative 1/16. So the terms are decreasing and they are alternating. So if the terms of the series are non-increasing in magnitude, so if they are decreasing, they are decreasing. And if the limit as k approaches infinity of a sub k equals 0, and is the limit as k is approaching infinity of 1 over k squared equals 0, yes. Well, if these two are satisfied, then the series converges. Now, we don't have to give these values all the time to look at the terms, and actually we don't know what happens from a specific term on, so we want to actually prove that these terms decrease in a mathematical clear way. So I'm going to show you how to do that using the derivatives. So let's say if f of x equals 1 over x squared, let's say we have this function, and taken from the fact that our series, except the term negative 1 to k plus 1, it's 1 over k squared. So f prime of x, it's negative 2 over x cubed. And if I make a table of values to see what's the sign, so x, f prime, and f, at 0 we have actually an asymptote, right, a vertical asymptote. And now, if we go to the left of 0, f prime is going to be positive, right? You just give a value, negative 1. If you plug it in f prime of x in here, you're going to get a positive function. And if we give a value to the right of 0, like 1, we get negative. So what does that tell us? It tells us that the function is increasing and then it's decreasing. So basically, our terms for values that are positive, right here on this region, our terms are decreasing. Right, so this function here, it's a function that is decreasing. So again, if you are wondering why I actually chose my function f of x equals 1 over x squared instead of negative 1 to n plus 1 or something like that, is because in this property here, we have the terms of the series are non-increasing in magnitude. So basically negative 1 to k plus 1 over k, or in our case it was k squared, in magnitude it's actually 1 over k squared. So we are interested only with what happens to the positive values if they are decreasing. And that happens, and we actually proved it using the first derivative. Now, we'll skip the remainder in alternating series. Let's take a look at other properties. Absolute and conditional convergence. So keep in mind, assume the infinite series sum as a sub k converges. The series sum as a sub k converges absolutely if the series sum of a sub k in absolute value converges. Otherwise, the series a sub k sum as a sub k converges conditionally. So now we have two words. We have converges absolutely if sum as a sub k converges in absolute value, and if it converges all with no restrictions, we say conditionally. So let's look at this example. Sum as k goes from 1 to infinity of negative 1 to k plus 1 over k to the second converges absolutely because sum as k equals 1 to infinity of absolute value of negative 1 to k plus 1 over k squared equals sum as k equals 1 to infinity of 1 over k squared. So it converges. This one also converges because of the p series, right? The actual p value equals 2. So these are series that converge. This example, it's also an example where this function, this series, converges absolutely, but we just proved here that it converges regardless if I put absolute value or not, because the terms of the series are non-increasing in magnitude, so it's actually convergent conditionally as well. So both of them are satisfied. Now another one, this one is actually sum as a sub k converges, then sum as a sub k converges, and if sum as a sub k diverges, then sum as a sub k in absolute value diverges. Now, in your textbook at page 701, the text updated since I made my presentation, has a summary of all convergence tests. So we are going to have a lot of convergence tests in this course, and it's good to know that there is a page in the book where it has everything put together. So now let's look at a few problems. determine whether the following series converges. And the problem is this one, sum -1 to the k over 2k plus 1. And so a sub k is -1 to the k over 2k plus 1. 4k equals 0, 1, 2, 3, and so on. So the terms of the series are 1, -1/3, 1/5, -1/7, 1/9, which are actually approaching 0. So, but more than that, they are also decreasing in magnitude, right? So we have 1, then we have 0.3, and then we have 0.2, and so on, which we can actually prove again by doing f of x equals 1 over 2x plus 1. If we do the first derivative, we actually end up with 2 over 2x plus 1 squared. And if I make a table of values for x and f prime and f to figure out where is increasing or decreasing, I actually have -1/2 as a vertical asymptote, and the f prime is positive everywhere. Just look at the function, it's all squared and all positive. So the function is increasing and then it's increasing again. So what is the problem? This would be a nice example to think of. So we saw that the terms are decreasing, and then here I am proving that they are increasing. Well, the problem is my first derivative. So the first derivative, it's actually -2 over 2x plus 1 squared. Just try and do a quotient rule. So when that happens, it means actually my values here are exactly the opposite. My function is actually negative everywhere. So it's decreasing and decreasing. So basically, our terms from 0 on, from here, are actually decreasing. So not just by giving values, we actually proved it by doing the work. And here, just because when you can do absolute value of a sub k, you get this term and it's approaching 0, then we can say that the series converges absolutely. Now, if we take a look at this problem and we consider this our term a sub k and we calculate the absolute value of that, we get this term. And if we calculate the limit as k is approaching infinity of absolute value of a sub k, we get 1/3, which is not 0. So basically our series diverges based on divergence test. I didn't even do the comparison, the alternating series test anymore. Another problem is sum as k equals 1 to infinity of -1 to k plus 1 over k cubed. Again, if we calculate the absolute value, we end up with 1 over k to the third, and this converges because it's a p-series with p equals 3, which is greater than 1. So you see how we are talking about the alternating series, but at the same time, we employ the other convergence test that we learned before. So this converges absolutely just because we did the absolute value and we figure out a new series with a new convergence test. But if I actually wanted to use for this specific problem the alternating test, so or using the alternating series test, which is our lesson, right? I can say that the terms right in magnitude are 1, 1 over 8, 1 over 27, and so on. And I can see that they are decreasing. And I can also say that limit as k is approaching infinity of 1 over k to the third equals 0. So decreasing and or non-increasing and 0, it actually makes that the series converges based on the alternating series test, like